Hello again, everyone. So today we're going to have another guest lecturer. It's Brian Condenzaro. He was a student here for a long time, and now he's moved on to Nvidia research, and he's going to talk to us about the GPUs, which are his area of research.
Okay. So I'm glad to be here. It's fun to come back to Berkeley and talk about GPUs and CUDA and OpenCL. So like Rosman said, my name's Brian, and please feel free to interrupt me at any time. I would so much rather talk about what's interesting to you than just like read through slides. So like interrupt me if if you have any questions or anything. All right, so what we're going to be talking about today is heterogeneous parallel computing. Most of the time when people talk about parallel computing, they talk about like big supercomputers and clusters where you have a whole bunch of CPUs. That's been what people did for many decades. Since, I don't know, probably about coming up on 10 years now, we've started to see this trend towards heterogeneous parallel computing where we have both collections of latency optimized CPUs as well as throughput optimized cores like GPUs. And these two kinds of processors work together in a system. We have the latency optimized cores. The traditional CPUs are really important because there's a lot of latency sensitive tasks that need to be performed, like running your operating system, dealing with the network, file I/O. A lot of these things, there's a huge amount of infrastructure invested in them, and it's really important. Additionally, some algorithms have really latency sensitive parts. So they have critical paths where you may have like large amounts of parallel work, and then you have a section where it's fairly sequential, and you need to minimize the time that it takes to get through that section in order to get parallel scalability. So latency optimized processors, traditional CPUs, are super important, and they're not going away. What I'm going to be talking about is how to use throughput optimized GPUs as a complement to latency optimized CPUs. And so the idea behind a GPU is that we're going to throw away the sequential performance. We're going to have really, really bad sequential performance, but we're going to make up for it in aggregate. And the way that I always like to introduce this topic is by showing pictures of actual chips, because at the end of the day, we actually have physical objects that manifest these two philosophies. So on the left-hand column, I'm comparing Ivy Bridge EX, which Intel just started talking about a couple weeks ago. So this is a brand new one from Intel. And then on the right column, I'm going to be talking about Nvidia's Tesla K40 processor, which is also fairly recent. And so we can do kind of a nice little compare and contrast so that you guys can get a sense of what the purpose of these architectures are and when you might want to use one, when you might want to use the other. So the first thing to note is that the clock speed on the traditional CPU is a lot faster, so it's somewhere around 3 gigahertz, whereas the clock speed on the GPU is a lot slower, around 750 megahertz. So, right off the bat, we notice we're going a lot slower. Interestingly, both this particular Ivy Bridge processor and the Tesla K40 have the same number of processing units, or cores. They both have 15 of them. And if you look on the die photos here, you can actually see them. The cores on the Ivy Bridge are the rainbow noisy looking things, and you can see there's 3 columns of them, and each of those have 5 cores each. And in the Kepler GK110, which is the processor behind Tesla K40, there's also 15 SMs, which we call streaming multiprocessors. This is our sort of indivisible unit of computation. And those are also arranged. They're actually arranged in groups of 3. There's 5 groups of 3. So one of the groups of 3, for example, is this little corner right here. You can see 1, 2, 3, 4, 5. And then this stuff in the middle is cache and memory controllers and stuff like that. If you also notice on the Ivy Bridge, so the rainbow-looking things are the cores. Then the columns of green that are next to those rainbow-looking things, that's actually cache. So you can see that a large percentage of the die area on the Ivy Bridge is cache, and that's really useful for a lot of workloads. So let's dig down a little bit deeper. So let's talk about how much parallelism it takes to fill one of these chips. And I'm including SIMD parallelism in here, which I'll talk about a little bit. But basically, you're probably familiar with it from your homework assignment. SIMD is single instruction, multiple data, right? So you're trying to do vectors of work at each instruction. So if we look at the Ivy Bridge processor, it has 15 cores. Each of those cores has 2 threads that can sit on it at the same time, sort of simultaneous multi-threading. And each of those has 8-way SIMD if we're talking about single precision floating point data or 32-bit integer data. So if we multiply all of that out, if you wanted to write a parallel program that used all of this processor, used all of its pieces, it's like 240 strands of work. So the sort of metric of how much parallelism you need to fill this chip is about 240. In contrast, on Kepler, we have 15 cores, it's the same number of cores, but each of those cores, instead of holding 2 threads, holds 64 threads simultaneously. And each of those threads, instead of being 8 wide, like you get with AVX, is 32-way SIMD. So if you multiply those numbers together, we have like order 30,000, 31,000 strands of parallelism that's needed to fill one of these chips. So that's like 2 orders of magnitude. And that's that's the programming challenge right there. So you can see right from looking at that number that the kind of code that you're going to run on this GPU is quite a bit more parallel. So you're going to need a lot of fine-grained parallelism in order to fill this chip. And that's going to have implications on the programming model and how you write code for it. So that's what today's lecture is on. Okay, so let's look at some throughput metrics. The first is single precision floating point operations per second. So the Ivy Bridge EX has about 700 floating point operations per second. The K40 has about 4.3 teraflops. So it has quite a bit more single precision throughput. And to go along with that, it also has a lot more memory bandwidth. So the Ivy Bridge processor has about 85 gigabytes per second of off-chip memory bandwidth, whereas the Tesla K40 has about 300. So those give you an idea of the performance improvements that you could potentially expect from using one of these throughput machines. The aggregate throughput can be quite a bit higher than what you would get from a traditional processor. And along with that, the energy efficiency is quite a bit better. The reason why we're having this shift towards heterogeneous processing is not because people intrinsically love GPUs, right? It's not because people really love writing super parallel programs. The reason why we care about parallelism is because of energy, right? Because we can't get traditional scalar sequential programs to run faster without spending ungodly amounts of energy. We have laws of physics that have impinged on our dream of writing sequential code. So that's why you're all taking this class, right? Is because of energy, right? And so the picojoules per operation on one of these throughput machines is quite a bit better than what you would get on a traditional latency optimized core. And that's what allows us to scale it up and have higher aggregate throughput numbers. And as I mentioned before, this comes at a sacrifice. The performance of any one of these threads is going to be quite a bit lower. Okay, so then the next thing that I wanted to take a look at is the memory hierarchy. So the memory hierarchy on throughput machines tends to be kind of inverted compared with what you get on a traditional latency optimized processor. So let's see, you guys had your first homework assignment already. Was it matrix multiply optimization? Sweet, that's the best first intro to CS267. So did you guys try running matrix multiply without any cache blocking? So what was the experience like? Tell me how it went. So okay, so then you cache blocked, and how much faster did it go? Like 5 times faster, or something like that. Okay, so you guys are already familiar with the impact of using the memory hierarchy correctly, right? And what happens if you don't. So a CPU memory hierarchy is kind of like a pyramid where you have registers that there are few of them, but they're really fast. And then you go down, there's the L1 cache, which is quite a bit bigger. And then the L2 cache, which is even bigger. And then the L3 cache, which is huge, right, aggregated across the whole chip. When we look at this Ivy bridge and I say, oh, those green things are cached, that's actually just the L3 cache. If we look inside of each one of those rainbow cores, you can see on the corner over here like this is probably the L2 cache. And the L1 cache is smaller. You can't really see it. And the register files are distributed. You can't see those either. OK, so that's the traditional way of doing it. And let's look at this memory hierarchy, on-chip memory hierarchy for this latency-optimized processor. We have some number of kilobytes of register file. It's not really clear exactly how many because there's architectural register file that you can see with a compiler, but then there's physical register file that the processor uses to do out-of-order processing to sort of find more instruction-level parallelism that in your code than was actually there. So it's some number of kilobytes, maybe several hundred kilobytes, not sure exactly. Then we have the aggregate L1 cache. So each core has, I think, 64 kilobytes of L1 cache. And so that makes about a megabyte of L1 cache. Then we have the L2 cache. Each core has, I think, 256 kilobytes. So that's about 4 megabytes on aggregate. And then the L3 cache is huge. There's like 37 megabytes. So that's like awesome. And I love that, like 37 megabytes of cache on chip. That's like progress. That's Moore's law. That's, anyway, civilization in action, giving us, I mean, do you know how many transistors are in there? Each one of the bits in that has 6 transistors, and there's 8 bits in a byte. So you multiply that out. It's a very large number of switches, giving you that 37 megabytes of cache. Anyway, it's pretty good. So I want to contrast that with the GPU, which is kind of upside down. So the register file is actually the largest amount of storage on chip. So it's actually, by some strange coincidence, the aggregate register file on the GK110 is the same size as the aggregate L2 cache on this Ivy bridge. And so what that tells you is that when you're doing your performance optimizations and you're thinking about the memory hierarchy, the most important level of the memory hierarchy on these throughput-optimized processors is going to be the register file. And because of that, the way that registers work in these processors is different than what you get on a traditional latency-optimized core. Instead of having a fixed number of architectural registers, the amount of registers that you get for your program depends on the kind of program that you write. So if you write a program with lots of state per thread, it's going to use more registers. And that's going to impact the effective parallelism that you get when you're running your code, because the processor is going to pack as much work onto each core as it can fit. So if each thread is using more registers, then it's going to be able to fit fewer threads on each core. So I'll talk about that more later, but it's an important difference that most of the state that you can access is actually in register file. Okay, so then we go to L1 cache or local store. I was saying earlier that each of these cores has 64 threads, and each of those threads has 32-way SIMD, if we want to use the same terminology here. So if you multiply that out, that's like 2,000 strands of parallelism that's sitting on one core. So if we look at the L1 cache, which is 64K, it's actually not very much storage per thread, right? If you divide 64K by 2K, then it's not very many bytes per thread that you can fit in this cache. And because of that, the cache can be managed in software. And I'll talk about how to do that. But basically, when you're using these throughput processors, you need to spend more attention on what data is actually going to be sitting in that shared memory is what we call it. It's the same place as the L1 cache in the hierarchy. And yeah, so I'll talk about that more in a second. But that's also something that people spend a lot of time figuring out how to use correctly. And it's a fairly limited resource. And then finally, the last level of the cache hierarchy is this L2 cache, and it's really small. It's like 1.5 megabytes. So the L2 cache is smaller than the register file. So any questions at this point? I just hope this gives you kind of a sense of the kind of programming task that we have to set out on when we're using a GPU. It's a really different kind of machine than a latency-optimized processor. It has really high throughput, potentially, but you have to use it right. And using it's a little bit different. So, yeah.
I'm curious to what extent a company like Nvidia is designing architectures now with an eye toward high-performance computing as opposed to just graphics applications.
Okay, so that's a great question. We at Nvidia like to say that all of our high-performance computing processors have a day job, which is playing games. Because people pay money to play games, and the gaming market is actually really big and it's growing. The high-performance computing market is attractive, but it's always been sort of a graveyard of various companies. I mean, you can look through the history of over the past 30 years and how many high-performance computing companies have run out of money, right? So it's important to us that our processors have a day job, and that's primarily where most of our revenue comes, is from playing games. I don't actually play that many games. Sometimes that makes me feel weird working at Nvidia, but so I would love it if the situation were reversed, right? If most of Nvidia's revenues were coming from people like you and me that are programming these GPUs to do high-performance computing. However, that's not the case, and historical trends tell me it's probably not likely to become the case, just because other companies that have tried that haven't really succeeded in the long term. So, you know, our processors are first and foremost graphics chips. Having said that, graphics is a very interesting workload because, number one, it's like practically inexhaustibly computationally intensive, right? Because you and I are really good at noticing that images that are rendered on a computer aren't quite right. And the only way we know how to fix that is by doing more compute in order to make the pixels look better. So there's still a lot of work to be done, and a lot of more compute that's going into graphics. It's also very parallel. You know, graphics chips started out, you run a program for every pixel on your screen, right, to figure out what color it should be. So it's a super parallel workload. It lends itself to throughput computing. And it's the reason why GPUs have this throughput architecture, is because it's a natively parallel processor. The workloads that it's built to run from day zero are all completely parallel, where we have huge amounts of parallelism. So because of that, I would say, you know, having this graphics heritage is a blessing and a curse. It's a blessing because it keeps the projects, you know, solvent. Our chips have a day job. It's a blessing because a lot of the goals of graphics are the same as compute. There's lots of high, computationally intensive things that we need to run. And it's also a blessing because graphics is power constrained, right? Like, we can plunk down cores, and we know we'll get scalability because there's lots of pixels. But ultimately, we're constrained by power. And so that forces graphics architectures to confront power issues really, really carefully. And I think going forward, since every part of computing, the computing industry, is dominated by power and energy concerns, it's good to have that focus, right? We can't get away with an energy and efficient processor. So yeah, hopefully that answers your question. All right. Okay, so why do we care about heterogeneity? I've just gone through this long explanation of how they're different, but why should we care about it? Why should we want to use this different thing? The answer is because the different goals produce really different designs. The throughput cores assume the workload's really parallel. Latency cores assume the workload is mostly sequential, and you have a few threads maybe to add parallelism. The goal of a latency-optimized core is to minimize the latency experienced by one thread, so we have lots of big caches, and we have really sophisticated control mechanisms that do things like guess whether a branch is going to go this way or that way, with lots of on-chip state that looks at the history of every time we've taken this branch in the past and guesses and predicts what it's going to be next time we take it in the future. And lots of out-of-order processing, where we're reordering the instruction stream dynamically to reveal more instruction-level parallelism. All of this makes the latency of a single thread lower, but it wastes power because it takes a lot of energy to figure out all these things that we're computing about the instruction stream as we go through with it. The throughput goal is to maximize the throughput of all of the threads, so we can have a lot of arithmetic logic units. We can use multi-threading to hide latency. So instead of having 2 threads parked on a core, we can have 64 threads. And then when a thread goes to load data from memory, it can just be suspended and just sort of wait until the data returns from memory. It may take a long time for that data to return. So the latency of getting that request back would be important if we didn't have other things to do. But since we're a throughput machine, we assume that the core is always going to have some other piece of work to do. So when there's some long latency event like a memory request, we're just going to suspend that work and grab some other work that's now ready because, say, its memory request returned a little bit earlier, and then we can start processing its instructions and, go around round robin, servicing all the needs of all the threads. So this allows us to simplify a lot of the control, and it also pushes us towards larger SIMD. So now I'm going to talk about SIMD for a while. So SIMD architectures make use of data parallelism, and you guys already looked at it when you were doing your homework assignment. Did you guys actually use SSE or AVX instructions? Did you use intrinsics when you were writing them down? Okay, so you guys are experts at this. You guys know more about SIMD intrinsics than practically 99% of programmers out there in the real world. So it's a good skill to have. Now, we care about SIMD because of area and power efficiency concerns, because you can amortize the control overhead, the processor's figuring out what it should be doing. You can amortize that over a whole vector of data when you have a SIMD instruction. And so processors have been getting more and more SIMD. Even latency optimized processors have been adding larger and larger SIMD units just because it's a power effective way of getting work done. The downside of SIMD is that parallelism is exposed to the programming model. So it can be exposed either to the programmer if you're writing intrinsics, or it can be exposed to a compiler that tries to automatically vectorize your code to use those SIMD units. So I would claim that SIMD parallelism is traditionally neglected. So when you have most of the topics in a course like this, you're going to spend a lot of time talking about threading models like OpenMP. You're going to spend time talking about distributed cluster models like MPI. All of these models about how do we get parallelism out of our code are orthogonal to SIMD. Right? The model is I write my MPI code, and then I'm going to parallelize each thread that's working in my MPI process using SIMD instructions using some other mechanism like intrinsics. And why is it? Why is it that these programming models have neglected SIMD parallelism? Well, part of it's just because it's hard. It's hard for a compiler to use SIMD because the compiler has to statically prove, for example, that your data is vectorized. So if you're doing loads, SIMD processors typically require that the addresses that you're loading are contiguous, so that you're loading a contiguous vector or storing a contiguous vector. The compiler, if it wants to do a SIMD load or store, has to prove that statically. That can sometimes be hard. Sometimes it's data dependent. It may be that 99% of the time, dynamically while you're running the code, it would have been a vectorized memory access, but then there's a few corner cases where it's not. If the compiler sees that, then it has to face the decision, am I going to vectorize it or not, or am I going to have a vectorized path and a non-vectorized path and choose that dynamically? It's just the design space is pretty large. And so the most common solution for how to deal with SIMD parallelism has been either to pretend it doesn't exist and then pray that the compiler fixes it for you with an auto-vectorizer. And that involves usually some faith, right, on the part of the programmer that the compiler will do this. And auto-vectorizers have been around for 30 years, and they're always getting better. And they can do some really amazing things, but they fail in a lot of cases. And in those cases, if you care about vectorization, then you drop down into intrinsics. And intrinsics are kind of like assembly language. I mean, they're slightly better than assembly language. At least you didn't have to do register allocation when you were writing your homework assignment. But you had to be very explicit about each instruction and what it was doing, and it's pretty low level. And also, it requires a new code version for every SIMD extension. So here's a brief history of x86 SIMD extensions, and there's actually more of them than I could fit on this slide. So this is a simplified version, but basically things started out back when you guys were maybe not even born yet, I'm not sure, with MMX, which was like a 64-bit set of 8-bit integer operations. And so you could have 8 of those packed into one 64-bit word. Then in the early 2000s, things picked up with SSE, where we got 4 times 32-bit floating point, and then SSE2, where we added double precision floating point, so we got 2 of those in a vector. Then we added SSE3, which added horizontal operations, like let's say we wanted to do a sum across a vector. Well, so SSE3 had that. And then there's like a whole bunch more, like supplemental SSE3, which is really hard to pronounce, SSSE3. And then SSE 4.1 and 4.2. And then there was AVX, which came out recently with Haswell, or maybe it was with Ivy Bridge, actually. So a few years back. Then there's AVX plus FMA, adding fuse, multiply, add, and AVX2, which added 256-bit integer operations and gather. And then sort of on the side, so this chain that I've given you is sort of Intel's mainstream latency-optimized core genealogy. But there's some other things too. So there's the Intel Xeon Phi, which they call a mini integrated core, and that has 512-bit SIMD, so it's even larger. It's like 16 elements if we're talking about single precision floating point. And then there is various other things, like AMD proposed their own set of SIMD extensions. Okay, so the point of this slide is to overwhelm you with the idea that every time there's a new SIMD extension, if you want to use it, you have to use a different set of intrinsics. That's not a very nice programming model, right? And so what I'm claiming is we need to do something about that. We need a programming model that is going to use SIMD natively, right? Now, I think one of the reasons why SIMD has been neglected as a form of parallelism for many years is that it didn't used to matter. So let's say that we had 4-way SIMD in SSE, so this is like early 2000s era. If you didn't use it at all, then you're limited to getting like 25% of peak of the machine. Actually, 25% is pretty good. What did you guys get on your homework assignment with matrix multiply? Did you 63? 71. So how long did it take you to get to 71? It took several days. So it was a lot of work. Actually, like getting 71% of peak is awesome. Like that shows you guys did a good job, right? As Berkeley students always do. But for the vast majority of code, people are probably getting like 1% of peak, and they just don't even know, right? They just don't even care. So if they are limited to 25% of peak because they didn't pay attention to SIMD, it's just in the noise. It just really doesn't matter. And so I think that's the reason why SIMD has been neglected, is because for a long time it didn't matter. But now we're in sort of this many-lane era where the SIMD vectors keep getting bigger, even on latency-optimized processors. So like Xeon Phi, for example, as I mentioned earlier, has 16-way SIMD. So if you don't use SIMD there at all, now we're talking about getting 6% of peak as your maximum. Your upper bound on what you could get. So you can see that neglecting SIMD gets more expensive. Nvidia's processors are 32-way SIMD. AMD's GPUs are 64-way SIMD. So you can see how these throughput optimized cores had to confront the SIMD problem from the beginning, because it just wouldn't be feasible for us to ship a graphics part that got 1/32 of its peak performance because the compiler didn't manage to vectorize a loop, right? We have to get everything vectorized in order to get things up and running. And so the programming model that we use for these throughput processors needs to address SIMD parallelism, and it also needs to address thread parallelism, because we need lots of threads too, right? So we need the programming model to do both. And that's what the CUDA programming model is designed to do. So CUDA is Nvidia's programming model for how to program our GPUs. OpenCL is a standard programming model for programming everybody's throughput optimized machines, including things like FPGAs and other things like that. So I'm going to be talking about that too. I'm going to introduce things from the perspective of CUDA because that's what I started using. It came out first. And OpenCL basically has a nice correspondence with CUDA terminology. So I'm going to explain things using CUDA terminology, and then I will explain the correspondence with OpenCL terminology. And when you guys do your homework assignment that uses GPUs, I assume the TAs are going to help you figure out exactly how to go about programming it. Okay, so I always like to start out programming model talks with code because, I mean, that's where the rubber meets the road, right? Okay, so this is the hello world of data parallel throughput-oriented computing, which is adding two vectors together. So it's just an element-wise addition. Okay, so there's a couple things that I want to point out here. First is that we've got, in CUDA, we have a unified model where you have throughput code intermixed with latency code in the same file. So how are we going to use the CPU and the GPU together to solve a problem? Well, we're going to write code, and the code can coexist in the same file and refer to each other. So basically, your int main here, that's your standard C routine that is one thread that runs when you run your C program. And what we're going to have it do is launch a CUDA kernel. So we call functions that you launch on the GPU, we call those kernels. And we're going to launch it in a configuration of parallel threads. So we're going to and I'll explain more about what it means in a second. But basically, you see those three chevron brackets after vec add, it says bracket, bracket, bracket. That's the parallel configuration. So you're saying, this is my organization of threads that I want to launch this program on the GPU with. And then you give it the parameters to the GPU. Okay, so now we can look at the function that's actually running on the GPU, vector addition. It's taking 3 pointers, just pointers to memory. And the first thing that it's doing is figuring out which element this program is being invoked on. So every CUDA thread, which is going to be mapped onto one SIMD lane of this processor, can have its own index. And so that's called like thread index. The threads are in blocks. I'll get to this in a second. But basically, you can figure out what your index is. And then the line of code that actually does the work is just what you would expect, right? We're just dereferencing the destination vector with that index and adding the two elements from the two source vectors. Okay, so this is the hello world of CUDA programming. And we'll get back to it in a second because this code is actually buggy. So I'm going to ask you guys to find the bug after I explain things a little bit more. Okay, so what does a CUDA program look like? It's a hierarchy of concurrent threads where we have parallel kernels that are composed of many threads, and all of the threads are going to execute the same sequential program. So we're going to write code for one of these threads. The threads are grouped into blocks, and the blocks are going to be of limited size, like only up to, say, 1,000 threads in a block. And threads that are in the same block can cooperate. They can share data in on-chip memory. They can synchronize. They can assign each other to do things. Threads outside of the block need to be independent. And I'll talk about that in a second as well. And then, so every program starts out figuring out who it is so that it can then proceed to do work differentiated based on its index. So you have to have a unique ID in this model. Okay, so what is a CUDA thread? It's an independent thread of execution. Conceptually, it has its own program counter, so each of the threads can do different things. Despite the fact that they're going to be mapped onto a SIMD processor where the actual SIMD execution is sort of ganged up into the SIMD vectors, when you write code for this, you don't worry about that. You just write code for one of the lanes of this vector, which we call a thread, and let the hardware do the vectorization. So the GPU has a lot of hardware support for dynamically vectorizing your code. A CUDA thread has no implication about scheduling. In fact, you can't even assert that this thread and this other thread are going to be executing and co-resident on the chip at the same time. So you can't synchronize between arbitrary threads because they may be executed sequentially. The hardware has a work distribution unit that may decide to execute thread 0 and then finish thread 0 and then execute thread 1,000. And if you wanted thread 0 and 1,000 to synchronize, they would need to be concurrent. But the hardware does not guarantee that. I'll and I'll mention that a little bit more later. Okay, so what's a thread block? A thread block is a small group of threads, and by small, for GPUs, that's like 1,000 or several hundred threads. And all of the thread blocks in the kernel start at the same place, but they can execute any code that you want. So you can just say, like, if my block index is this number, then execute algorithm A, and if my block is this other number, then execute algorithm B. The important thing, like I mentioned earlier, is that they have to be independent, and your program has to be valid for any possible interleaving of these block executions. Okay, so the kinds of parallelism that we get with this model, we get thread parallelism because each thread is an independent thread conceptually. We get data parallelism across threads in a block, across blocks in a kernel. And we also can have task parallelism because different blocks are independent, and also because we can do multiple kernel launches in parallel. So if we assert this kernel and this other kernel are independent, we call that streams. They can be associated with different streams. Then the hardware can actually execute different kernels in parallel on the same processor. So that's a form of task parallelism. Okay, so synchronization. Anytime you talk about parallelism, you need to talk about synchronization. Threads within a block can synchronize with a barrier, so we call our barrier sync threads. This barrier is an execution barrier, and it's also a coherence point, so all of the writes that are made by all of the threads within that block are visible to all of the other threads in the block after this barrier. So that allows you to do things like have thread 0 produce some piece of work that the rest of the thread block needs to use. Then you synchronize, and then the other threads can read that work that was written by thread 0 and go on to use it to get whatever they need to do done. Blocks can coordinate with atomic memory operations. So let's say, for example, we had a shared queue in memory, and we wanted to be able to append to that queue in parallel. We can use atomic memory transactions to increment the pointer, that's the tail pointer on this queue, and use the result to get a unique address for each thread that's appending to that queue, or each block, depending on how you write your code. So this allows for a certain amount of coordination. I mean, I was saying earlier that you can't synchronize between blocks, but you can use blocks to coordinate with each other to, say, collaboratively produce a data structure. And then we also have a barrier between dependent kernels, between kernels in the same stream. So let's say we have these two kernels, vec minus and vec dot. It is guaranteed by the hardware and the software that by the time vec dot begins, all of the work in vec minus will be completed and stored to memory and visible to all of the threads that start up in vec dot. So that's how you get synchronization across, something larger than a thread group, is that you just terminate your kernel, launch another one. Okay, so the blocks need to be independent. I keep repeating myself on this because it's an important part of the programming model. They might be running concurrently. They might be running sequentially. A shared queue pointer for coordination is fine, but a shared lock is probably a bad idea. I mean, you can write locks in CUDA using atomic memory operations like compare and swap, but because you can't guarantee that any thread blocks are concurrent with any other thread blocks, synchronization using such a lock is a little bit tricky. So I would suggest not trying to do that when you're first getting to know how to use CUDA. So why do we have this restrictive requirement about scalability, about independence of our blocks? It's because of scalability. So our GPUs we ship in a really diverse set of configurations. The number of cores can vary from like 1 core. Recently we announced the Tegra K1. It's a tablet processor, and it has 1 SM in it. And you can run CUDA code on it, but it's only got 1 SM. So that means that it can fit a certain amount of thread blocks on that 1 SM, and if you launch more than that, then it's going to be sequentially going through your program to finish all of those thread blocks. Our largest chip, GK110, the Kepler chip that I was showing you earlier, has 15 SMs. In the past, we've had up to 30 SMs. So the same binary targets all of these chips because when you write your code with independent thread blocks, you get scalability. You've partitioned your problem into sort of small digestible chunks, and then the hardware has a lot of freedom as to how that's actually going to be executed. So that gives you scalability. So that makes sure that CUDA programs are very scalable. Okay, so now we're going to talk about the memory model. We have a per-thread local memory. This is like stack space, right, for a traditional processor. We have per-block shared memory. So this is takes the place of the L1 cache or shares space on the chip with the L1 cache. And you use that for coordinating between threads in a thread block. We also have, every GPU has its own set of memory attached to it. It's really high bandwidth memory, fairly low capacity memory. And so data that you put in that memory is going to persist across kernel launches. So the way that you write code on a GPU, you move data to the GPU, you do some computation, which may involve a whole bunch of different kernels, and then when you're finally done and you have the result, say you wanted to visualize it or whatever using software running on your CPU, then you transfer the result back. But data persists in memory across kernel launches. Okay, and then there's a function in the CUDA runtime called CUDA memcopy that you use to actually move data between the GPU's memory and the CPU's memory. And you can specify which direction you want and so forth. Okay, so back to this hello world. Before I ask you to find the bug in here, I guess I should explain that the first parameter in this CUDA thread launch, in this triple chevron, is the number of blocks that you want to launch, and the second parameter is the number of threads per block. So the actual parallelism that you're requesting is basically the product of those two numbers. All right, so I've given you a hint. What's the bug in this code? Why is this? Well, there's lots of problems with this code, but what's one of the things that bothers you when you look at this code? Yeah.
What if n isn't divisible by 256?
Exactly. What if n isn't divisible by 256? What would happen? So a common CUDA idiom is that you're going to round up. So you're going to say the number of blocks that I launch is basically the ceiling of n divided by 256, right? And then you're going to need a guard around the actual code in here in the CUDA kernel, because in that case you're going to launch a few more threads than you actually need. And if you just tried to dereference elements of the vector, say in a vector add, you might get a seg fault, right? Because you might be accessing out of bounds. So then you need to add a little. If I is less than n, then ci equals ai plus bi. Otherwise, do nothing. So that's a common CUDA idiom. Okay, so let's talk about managing data. In that, another bug about this code is that DA, DB, and DC are not allocated, and so that would also lead to a seg fault. So let's fix that. So if you're using a malloc interface on the CPU, it's pretty straightforward, right? You just say, okay, n is 256 by 1024. That's how many elements are in my vector. I'm going to malloc data for the A input and for the B input and for the C output, and then I'm going to initialize my A and B. In this particular code snippet, the pointers are annotated with this H underscore to indicate host. This is just sort of a mnemonic for the programmer that this memory is host memory. So if you try to give this pointer to a GPU kernel, it's going to seg fault because the GPU can't, by default, read the CPU's memory. So what we need to do in order to get the data over there is we need to also malloc space for a copy of all of this data on the GPU, and we use CUDA malloc for that. It's basically the same kind of interface as normal malloc. And then we're going to use CUDA memcopy to move the data over. So in this case, destination is the device pointer, the source is the host pointer, the amount of bytes that we need to transfer, and then an enum that tells us what direction. So in this case, we're moving the data from the host to device, so we use CUDA memcopy host to device. Then we run the kernel, and then we do the memcopy in the other direction to get the data back. Now, you don't. I never use CUDA malloc or CUDA memcopy because there are C++ classes that automate this for you that I don't know if I'm going to have time to talk about, but it's not necessary to do everything at a low level like this. I mean, just as you probably don't use malloc all the time when you're writing C code, you probably use data structures that allocate themselves. You can do that for CUDA code as well, and that's what I recommend doing. depending on how much time I have. We'll see if I can get to that. Okay, so CUDA has minimal extensions to C++. First of all, we have a global function, which is a kernel that's callable from the host. So this is a thing that you can launch with that triple chevron parallel kernel launch. We have device functions, which are functions that are callable on the device. So you can basically, you don't have to write all of your code in one big function that gets launched. You can use, basic software engineering principles to break up your work into small functions and call them from the device. And you just need to indicate that that function runs on the device with this little device decorator. You can also indicate that a function is for the host as well. So one common idiom that I write code is, I often write my code in both a host and a device function. That way I can debug it on the host and then launch it on the device. So you can put both a host decorator and a device decorator on the same function, which is a really useful thing. Then we have global variables. If you want global variables, you can put a device in front of it, and that specifies the variable will live in the GPU's memory. And then an important thing is this shared decorator. That says this variable lives in per block shared memory. So that's how you're going to use on-chip shared memory, which is really important for coordinating between your threads in each thread block. Okay, so then we have this parallel kernel launch with triple chevrons, and I think we've talked about that a bunch of times, so hopefully that looks familiar by now. We also have some special variables for thread IDs, so like which thread am I in my thread block? That's a thread IDX. Which block am I in my set of blocks that's been launched? That's my block index. And what's the size of my block in terms of how many threads are there in my block? That's the block dimension. All of these ID variables are actually dim3 types, which indicates that they're three-dimensional. So depending on the type of problem that you're launching, it may be convenient for you to launch threads in, say, two-dimensional blocks or two-dimensional grids or three-dimensional. This is a programmer convenience thing. So just so you know, you can do that. I found it to be convenient. It's nice, especially if you're writing code that's for a naturally two-dimensional problem. You can do things like, I'm going to assign one CUDA thread to one output element of my problem, and the indexing just comes along with it. You don't have to like convert between a one-dimensional index and a two-dimensional index. It's kind of annoying. And then there's a few intrinsics that expose specific operations like barrier synchronization. But other than that, it's mostly just C++. Okay, so how do we use per block shared memory? This is an important part of writing fast CUDA code, is sharing data on chip between threads and block. We do that by putting this shared decorator in front of a variable. Most of the time it's going to be an array, like you're going to have an array, maybe say an element per thread in your block. You can declare that, and then you can have each thread compute something, store its data there, synchronize, and then all of the other threads in the block can read it. So that's how you can communicate values between threads. The shared memory, it shares space with the L1 cache. It's generally faster than accessing data through an L1 cache, but it's slower than the register file, and it's small. The register file is 2 to 4 times bigger. But it's an important part of writing good CUDA code. Okay, what kinds of features, what kind of code can you write on the GPU? There's double and single precision math, IEEE compliant. There's integers, characters, shorts, longs, longs, all the things you expect in a normal C program. There's standard mathematical functions that you might get in math.h in a C program, like sine and cosine and so forth. There's also atomic memory operations that allow you to coordinate between threads. So I was mentioning appending to a queue. You could also use, like, say, an atomic add for a reduction, right? It might not be the best way of writing a reduction, but you could just have each thread atomically add its value to the same location in memory, and by the time all threads complete, that memory location will hold a correct sum. So the ordering of how those summations happen is not guaranteed with atomic, so it might not be the right thing to do, but it's an important tool. Okay, and then there's functions that you call from the host, from your CPU program that's basically orchestrating all the work that's going to happen on the GPU. There's allocation, there's memory copies, and some other things I'm going to skip. Okay, so at this point, I'm going to ask if there's any questions about any of the stuff that I mentioned about CUDA, or if it sort of makes sense. Sort of makes sense. That's what I like to hear. Okay, so now let's talk about OpenCL. So OpenCL.
Question?
Oh yeah.
So just to point out, your memory hierarchy is not the usual one where it gets smaller as you go up. It's kind of reversed there, isn't it? Between registers and shared.
It is. We covered that before you came in.
Okay.
Yep. So Nvidia created CUDA, and people decided, hey, this is a pretty cool idea. We're getting pretty good results using it. We'd like to use it on other people's GPUs, not just Nvidia's GPUs. And so OpenCL is an effort that basically takes the things about CUDA that people like and democratizes them across other hardware besides Nvidia GPUs. Intel supports it on their CPUs and the integrated GPUs that are in a lot of laptops. Imagination Technologies, which does GPUs for your iPhone, for example, is at some point in the future going to support OpenCL. AMD supports it, and Nvidia supports it. And it's basically very similar to CUDA. There's a few differences. One of the differences is that it has a richer task parallelism model. So CUDA, I mentioned, has streams where you can declare this kernel and that kernel are independent by putting them in different streams. In OpenCL, you can actually do something more fine-grained than that. Instead of linearizing your independent work into separate streams, you can just declare a dependence graph, a directed acyclic graph of dependencies, and say, this kernel and this memory copy need to complete before I launch this other kernel. And you can dynamically sort of unroll this dependence graph, and the runtime will walk it in parallel for you. So that's kind of a nice feature that it has. So this slide, I'm not going to go over all of this. This is mostly just for reference. So a CUDA thread in OpenCL is called a work item. A CUDA thread block is called a work group, and so forth. But it's basically, there's a one-to-one correspondence between the kinds of things that you need to write in OpenCL and CUDA. Now, there's some other differences as well. So CUDA supports C++ features. Particularly, it supports C++ templates, which are a really important tool for writing parallel code because they allow you to separate sort of the skeleton of the algorithm that you're solving from the actual implementation. So you can instantiate your skeleton with a different C++ type using C++ templates and get a very different kernel out of it. So that allows for code reuse. OpenCL doesn't support any C++ features. CUDA is a unified programming model where your GPU code and your CPU code exist in the same source file, and they can be shared, so you have the same function that works both on the CPU and the GPU. OpenCL separates those, so your OpenCL code that's going to run on the GPU has to be in a different file, and you can't really share things in the same way that you do with CUDA. And then finally, OpenCL is a lot lower level than CUDA. So with CUDA, you have a compiled model where you have your .cu file. You type NVCC on your CU just like you type G++ to compile a normal C code. And it provides a binary for you. OpenCL, what you do is you put your GPU code in a file, and then you write CPU code that reads that text of your program into memory, and then gives the text as a string to the OpenCL runtime and asks it to compile it dynamically. Then the OpenCL runtime returns you an object that says, did the compilation succeed or not? If it didn't, then you need to ask the OpenCL runtime, how many bytes of error message do I need to allocate? And then you allocate the bytes for the error message, and then you ask the OpenCL runtime to copy the error message into your buffer, and then you print out the buffer that says, you had a syntax error on line 3, and then go through and edit your code. So basically, in CUDA, I showed you that triple chevron launch where it's a parallel function call, right? In OpenCL, what you have to do is for every argument to a kernel, you need to call a function in the runtime that passes the value of that argument and says, okay, Now I'm setting the value of argument number 1. Now I'm setting the value of argument number 2. So you do a bunch of calls to set the values, and then you do the call to actually launch the work. So OpenCL is a lot lower level. It's a lot more like an OpenGL API, if you've ever used that before, than CUDA, which is this integrated model. So, you know, there's pluses and minuses to both. I'm just trying to explain what they are. Okay, so another thing about OpenCL is that you can write code that targets really different kinds of hardware, but the actual implementation is going to vary depending on the runtime. I'm going to skip this slide just because we don't have time, but the important point that I want you to get is that with these throughput architectures, the low-level details of the architecture really matter in terms of what performance you get. And so even though you might have code that can run on a bunch of different processors, it's probably going to run slowly if you haven't tailored it to the architecture that you're targeting. And that's kind of just a side effect of we've gotten more efficient, but we've thrown away a lot of dynamic hardware that does the work for you of mapping your program to the architecture. Okay, so let's talk a little bit about imperatives for efficient CUDA code or OpenCL code. First of all, you need to expose abundant fine-grained parallelism. You need thousands of threads. You need to maximize your on-chip work using shared memory on-chip or OpenCL Scratchpad. It's orders of magnitude faster. We also need to minimize execution divergence. So if you have a branch and the branch is based on your thread ID and you branch in a way that breaks up the SIMD vector, then the hardware is going to serialize it. It's going to say, okay, I'm going to execute all the threads that went on the then branch, and then I'm going to execute all the threads that went on the else branch after I'm done with that. So it sort of sequentializes it. And as you keep on branching, you know, if you fully diverge, then you could have every one of your 32 threads in a CUDA group that we call a warp. You could have them doing different things, but then you've given up a factor of 32 in performance. So like we were talking about before, at that point, you're not getting any SIMD vectorization. The nice thing about CUDA is that if there's just a few cases, a few corner cases where you need execution divergence, you can have it, and the rest of your code is still going to run fast because the hardware dynamically will check for convergence and give you that vectorization. Also, you need to minimize memory divergence. So as your threads access memory, it's much better if they access it in a way that is vectorized. So if each thread, let's say thread I, accesses element I, and thread I+1 accesses element I+1, and so forth, then you get this vectorized memory access pattern where you're loading and consuming 128-byte cache lines all at the same time. That's going to be maximally efficient. Okay, I'm going to skip this. I'm also skipping this because we are really low on time. This slide, it gives you a bunch of things to look at for occupancy. I think you guys are going to post these slides, right? So you can refer to this in case you're interested. Basically, there's a lot of different things that can affect how many thread blocks get mapped onto a particular core. So the fatter the state in each of your thread blocks, the fewer of them are going to fit on a core. And we call that occupancy. So it's sort of this multidimensional problem with a lot of different kinds of constraints. And you're going to be limited by whatever your limiting factor is, and there can be a bunch of them. So that's what this slide shows. So if you're worried about why is my occupancy low, this slide gives you sort of a clue to things you might want to look at. Basically, how much state are you using? Are you using lots of registers? Are you using lots of shared memory? That kind of thing. There are profiling tools. So there's one called NVVP that I use a lot that gives you sort of a visual perspective on your program. So this is showing a bunch of different kernels running on a GPU, and you can see when they started and stopped. And you can drill down into each one of those kernels and look at performance counters that tell you, oh, this particular kernel was running slowly because you were accessing the cache in a non-vectorized way, so you're getting lots of divergent memory accesses. Or this kernel is running slowly because you had a lot of instruction divergence, which means your SIMD vectorization failed because dynamically the hardware found that your threads were doing different things. So then you can use that to improve the code that you write if you're interested. A cheaper thing to do besides running a visual profiler is if you export this variable CUDA profile equals 1 in your shell, it will, after your program's done, there'll be a log file that shows you each of your kernels, their occupancy, and their runtime. So you can use that. It's a sort of a cheap way of figuring out what's actually being run on the GPU. Okay, I'm going to skip this as well. All right, man, time is going by quickly. So Kathy Yellick, who's a professor here at Berkeley, defined a many-core processor as a device for turning a compute-bound problem into a memory-bound problem. And I really love this definition. So basically, if you have this throughput-oriented processor and it has huge amounts of parallelism, but it's still got one socket, and that one socket's talking to one pool of off-chip memory, then most of your workloads are going to end up dominated by your memory accesses. And that's definitely true with GPUs. So this little cartoon, is just showing you basically what I showed in the die photos at the beginning of the lecture, where we have so many ALUs, but they're still talking to one set of DRAM. So most of your code, when you first write it, is going to be memory bound. And so I have an explanation in here of how this works. I'll go through it quickly. So memory is SIMD 2. A lot of times people don't really see it that way, but virtually all processors have SIMD memory subsystems. Let's say that I want to load element 0 in an array. Well, what actually happens, whether you're on a normal latency optimized core or on a throughput core, is that it's going to go ahead and load a bunch of elements. It's going to load elements next to it for you because it's assuming that you're going to use them later on. And in a lot of code, that happens to be a good assumption. Like, let's say you're just sequentially iterating through elements of a vector. If you load element 0, there's a high probability you're going to load element 1 as well. And so the hardware just automatically does that. And they call this sort of vector that the cache operates on, they call that a cache line, and it has a certain width. Every processor has a certain width. So this has two effects. Firstly, if you access memory in a really sparse way. So let's say that I'm just accessing elements 0 and elements 4, and I never use elements 1 through 3 or 5 through 7. The hardware is going to go ahead and load all of those elements in 0 through 7 anyway, because that's what it does. It always loads them in chunks. But that means that the effective memory bandwidth that you're going to get is lower, because you're going to be throwing away 3/4 of the data that got loaded. You're not using it. So sparse accesses are bad. They waste memory bandwidth. And also, unaligned accesses can waste memory bandwidth as well. So let's say I just want to access elements 1 through 4. Well, it turns out that falls across 2 cache lines. And so it's going to load elements 0 through 7 anyway. And you're just going to get half of the effective bandwidth. Okay, so what I've told you is true for every processor, CPU or GPU. The way that GPUs work, though, is that you have these SIMD lanes, and they're all issuing loads to whatever instructions that or whatever addresses that they are loading from. And then the hardware dynamically sort of puts the pieces of the puzzle together to figure out the minimal number of cache lines that are required to load or store to off-chip memory in order to service those requests. So that's called a coalescer. And coalesced loads or stores mean that you're getting full memory bandwidth. Your effective bandwidth is the same as the actual bandwidth that you required. And that happens when you present a set of unit-strided loads. You have dense accesses and when you're aligned to cache line boundaries. So that's an important thing to think about when you're optimizing your code is, are my memory accesses coalesced? And the profiler will give you lots of information about that. And there's lots of documentation about how to make that work. I'm going to skip this. Okay, so we have 15 minutes, and I have a very large amount of slides, which I'm not going to get through. What I want to talk about is now some higher-level tools for programming GPUs. So what I've been showing you is, the lowest level interface that people use when they're writing code for GPUs. It's probably what you're going to do for some of your homework assignment. But there are other things too. And libraries are really important in parallel programming because it's really hard to beat code that somebody else has optimized. So you guys did heroic work to get 71% of peak on your matrix multiply, but did it beat MKL? did you try to beat MKL? So it probably didn't. And you know, Intel has an army of people in Nizhny Novgorod in Russia that do amazing work on optimizing GEM on Intel processors, right? So it used to be true that if you wrote more abstract code, it would go slower because you're at a higher level of abstraction, you're introducing inefficiencies. But with parallel programming, I'd actually say we also have this concrete tax. If you write too much low-level code and somebody else has already done a library for it, then your code is going to be slower than if you had written the higher level code. So this actually may be a little counterintuitive, but basically, you know, if you can use a library, you really should. It also gives you portability. So if you write low-level code that is specialized to one particular architecture, and then you run it on another architecture, you may end up getting something really slow. And here's an example of it, but I'm going to skip it because we don't have time. So basically what I'm trying to convince you of is that as we jump into this world of heterogeneous computing and highly parallel computing, we need a lot of libraries that make it able for you and I to reuse the great work that other people have done, figuring out how to map their computations onto these parallel architectures. And so libraries are a really good way of doing that. Nvidia ships a BLAS library, so this is a basic linear algebra subroutine library, so it has matrix multiply and friends in it. It's called cuBLAS, and it's free, and you can use that. We also ship an FFT library called cuFFT. And if you need an FFT, then you should use that. And then there's also another library that I'm going to talk about called Thrust that I'm a big fan of. It's a C++ template library, and it mimics the C++ standard template library if you've ever used that before. So this has containers and it has algorithms. So containers help abstract this GPU memory problem that I was talking to you about earlier, that you have to allocate a copy on the GPU's memory and then you have to manually move the data back and forth if you don't want a segfault. Thrust containers do that automatically. So you just say, I have this device vector, and you can dereference it and look at an element on the host, and it will do that memory transfer for you automatically. You don't have to worry about it. There's also algorithms. So like writing a parallel reduction is hard. Writing a parallel prefix sum is even harder. And writing, you know, parallel sort is, you know, the subject of many PhD theses, right? It's like 6 years of work to do a really good parallel sort. But you can access a parallel sort if you call thrust sort. And you get the benefit of all the work that these other people have done. Okay, so this is what a thrust program looks like that runs on the GPU. First, we declare a host vector of type int, and we're going to say it's holding 32 million elements. Then we call thrust generate, and that's going to basically call it takes a pair of iterators, a begin and an end, that form the range that you're going to be generating data into. And then it takes a function that you're going to call at each element. So here we're just passing the standard C rand function. So at the end of that thrust generate call, we've now filled this vector with random numbers. Okay, then transfer the data to the device. We say thrust device vector of int, and then you just do an assignment from the host vector. And that automatically allocates the data and moves it for you. So that's why I never call CUDA malloc or CUDA memcopy, because like I can just include thrust device vector.h and do that. Then we can call thrust sort. So this version of sort, you know, we just give it two iterators, a begin and an end iterator of the range of data that we want to sort. And we get a super high throughput sort and use the result of Dwayne Merrill's PhD thesis, which is really awesome. Okay, yeah?
Does that only run on Nvidia?
Yeah, so Thrust takes advantage of a lot of features that are only in CUDA and not in OpenCL. So it only runs on Nvidia GPUs. It does not run on other GPUs using OpenCL. However, it does run on CPUs using OpenMP and Intel thread building blocks as its parallel backends. So you can write Thrust programs that run in parallel on CPUs in that way. And I do that all the time. Okay, so let's see.
Quick question.
Yeah.
Is there any reason that you're discussing thrust as opposed to CUDPP? or anything like that?
CUDPP is a library of algorithms, and it basically sort of a precursor to Thrust. I prefer Thrust because it's a higher level interface. I mean, CUDPP is more like a BLAS level interface. Thrust is more like the C++ standard template library. So it's basically like a C++ interface versus a C interface. I think it makes it a lot easier to use, and that's why I'm talking about it. Like Thrust, for example, if you look at this line that says dvec0 equals 13, you can't do that in CUDPP. I mean, what that line is doing is actually pretty sophisticated. The C++ compiler knows that the type of dvec is a device vector, and it knows that when you assign to a device vector using the assignment operator, then you're going to need to call CUDA memcopy in order to transfer the data. So that is a lot of abstraction in one line of code. So it's really nice to be able to do that. Or the opposite here, where we're reading values back from the device on the last line of code. If you don't use Thrust, then you're going to be manually moving all of that data around. Or you're going to get a seg fault because you dereferenced a GPU pointer on the CPU, which I've done many, many times. So using Thrust prevents me from getting those seg faults because I don't have to write that code. Thrust is built around iterators, just like the standard template library. A pair of iterators defines a range, which is sort of the building block for algorithms. So like reduce, for example, if you want a parallel reduction that's going to sum all of the values in a range, you give it a beginning and an end. And that'll give you the sum. You can use iterators like pointers. You can increment them. You can dereference them. You can subtract them. This is what you can do with normal iterators in C++. I'm going to skip this. OK, so there are quite a few different algorithms in Thrust. For each and transform are basically invoking a function in parallel on a range. Gather and scatter are doing sort of indirect memory accessing. Reductions, there's different kinds of reductions, including reduce by key, which takes two ranges. One is sort of a key range, and another is a value range. And the result of reduce by key is that all of the values that have identical key values become reduced together. So that sort of lets you do a data-dependent set of multiple reductions in parallel. It's a really useful thing. Prefix sums, sorts. So we started out with vector addition in CUDA, right? This line of code right here is vector addition in Thrust. You have you call Thrust transform. You have a range of begin and end from vector A, and you have the begin from B and the begin from C, and you instantiate it with a functor. Here is plus defined to work on integer operations. So if you want to write your own functor that does some element-wise computation and you want to invoke it on parallel, then you could just put your own functor in here that you define somewhere else that can do something very arbitrary. And all of the work about, let's see, do I need to round up to figure out how many thread blocks to invoke? That happens for you automatically. So that's pretty nice. OK. Yeah, I'm going to skip this. You can provide your own types and your own operators. So for example, if you wanted to sort two floats, so like you have vectors of floats and you want to sort them based on their first element, you could create your own functor that's going to compare the two sets of two float vectors based on their first component. And you'll notice that it's overloaded as it's both a host and a device function, which means that this code can run on the CPU as well as the GPU. And Thrust will invoke it on the CPU or on the GPU based on the types of the range that you give it when you say sort. Interoperability, so Thrust iterators can be converted to raw pointers. So let's say that you wanted to write your own kernel for the homework assignment. You could still use Thrust to do memory allocation and data movement for you. You can just grab a pointer from the iterator. OK. And I'm going to skip this as well because we've already talked about this. This set of slides is just sort of driving home the point that there's a lot of code reuse when you use a parallel library like this. Like when you write sequential reductions, you don't even really think about it. You just, like, everybody just writes it. It's a for loop. It takes 3 lines of code. It doesn't matter if you're doing a sum or a product or a maximum or whatever. The code is pretty simple, and you've all probably written it a million times without thinking about it. If you want to write it in low-level CUDA, then it becomes, I'm not even showing most of the code because we have to do things like partition the vector into small groups that are going to be operated on by a thread block, have a thread block load its partition of data into on-chip shared memory, and then you have a parallel reduction tree amongst all the threads in your thread block, and then you store those out into a temporary buffer that then contains partial reductions for each of your thread blocks, and then you launch another reduction kernel that's going to sum up those partial reductions to get you your final result, right? So it's just a lot of work. So don't write your own reduction. Use thrust reduce. Sort is a really powerful parallel primitive. It can get rid of a lot of irregularity by grouping things together that share whatever properties you're interested in. So this is an important tool for getting rid of divergence, both instruction divergence as well as data divergence is use sort. And thrust sort is pretty good. It's way faster than what you get with standard sort or Intel thread building block sort. And it's smart, so it will use radix sort for you if your type is radix sortable. If it is radix sortable and your keys have low entropy, so there's not very many different kinds of keys, then it will sort faster. That's what this graph is showing you, that as the entropy in your keys gets larger, the throughput drops. So basically, like, you don't have to worry about this if you use thrust sort. Other people did. Sort with reduce by key is like a poor man's MapReduce. If you've ever heard of Google's MapReduce, basically the idea is there that you write a parallel function that's the map, and then it produces a key and a value pair for each invocation, and then you call reduce, and it groups all of the keys with the same value together, and then performs an operation on their associated values. Well, that's what reduce by key is. So sort plus reduce by key is a really powerful primitive. You can use it to do like histograms, for example. And thrust is on GitHub. It also is installed automatically with every CUDA installation. So, okay, that's my whirlwind tour of thrust. In summary, I hope that today you've learned, okay, we have these different kinds of processors. We have throughput processors. We have latency processors. I hope you've gotten a feel of what the difference is, what the programming model implications are, what tools you have for getting your code to run efficiently on throughput processors. And with that, I'll take any questions.
I'm wondering if you can comment at all on optimizing applications that are attempting to heavily use the CPU and GPU at the same time, and optimizing them such that the work is distributed and timed appropriately to allow full throughput in both of those architectures.
Right. So that's an important topic. CUDA is definitely, and OpenCL both are definitely designed to allow you to do that. I don't think they give you a lot of tools to necessarily solve that problem for you. I mean, I think it's kind of an advanced problem to try to solve. Basically, you end up running your CPU profiler and your GPU profiler, trying to figure out what your bottlenecks are. I think from a higher level, rather than just like what tools do you have to solve that problem, I think the higher level point is that things that you would want to run on a throughput optimized processor like a GPU are typically embarrassingly parallel, and the control flow is typically simpler. So things that are well structured, you would want to run on a throughput core. Like a matrix multiply is a great thing to run on a throughput core. A web server is not a good thing to run on a throughput core because it's going to be really branchy and you're not going to get a lot of SIMD. And so I guess as you work with these processors, you develop sort of an intuition about how to divide the workload. And typically, I think that intuition is good enough. I mean, the value of heterogeneity should be obvious, or else you won't use it, or else you'll just use traditional CPUs. right? So if it's confusing to you about should I put this on the GPU or on the CPU, then probably just put it on the CPU, and that's a good place to start. Things that go on the GPU, it tends, after a while, it tends to be pretty obvious that this thing is regular, it's high throughput, it's very parallel. I'm going to put that on the GPU. And in general, I'm skeptical of that. People propose all the time different programming models that automatically load balance between the two. So you have like a monolithic task, say a matrix multiply, and it tries to like parcel out the work dynamically to run on both the CPU and the GPU. I'm skeptical of that because it's an Amdahl's law problem. I mean, if heterogeneity is actually bringing value, if the GPU has really much higher throughput, then adding a small amount of extra throughput from the CPU isn't going to change the overall throughput. But it comes at a great increase in complexity of your programming system. So I'm skeptical of that. So some people might like that idea, but I think that's yet to be proven. Let's put it that way. Great. Any other questions?
Just a quick follow-up comment on that. If you're slightly less regular than matrix multiply and are doing Gaussian elimination, say, then balancing between the CPU and the GPU does turn out or has turned out to be a good idea.
It absolutely can be a good idea. I mean, all of the LinPack benchmarks that people run on supercomputers have to do this, and it's very important to performance. But I would say that's a more advanced topic. I would say when you're starting out, you should do the simple things on the GPU.
And on that note, let me just add that the next 2 lectures we'll be going back to talking about the 7 dwarfs, and the next 2 lectures will be on linear algebra.
Great.
Any more questions? Okay, thank the speaker again.